I've recently taught my homebrew 8-bit CPU how to do addition. That's nice and all, but it would be fantastic if we could also do subtraction. And the solution is extremely straightforward. We don't even need a circuit to do the subtraction. In fact, all modern computers have no idea what a negative number is or how to do subtraction in general. But they're very good at faking it. So let's look at how they do it. In an earlier video, I built a 4-bit adder using just logic gates. So let's look at 4-bit numbers and how we can do subtraction with them. 4 bits can hold the numbers 0 to 15, in binary 0, 0, 0, 0 to 1, 1, 1, 1. Imagine the numbers 0 to 15 as just a line. When we add numbers, we just walk towards the right on this line. So say we want to add 2 and 3. We start at the number 2 on the line and walk 3 steps right. 1, 2, 3 steps takes us to the number 5, which is the result of adding 2 and 3. To add another 4, we walk 4 more steps to the right. So 1, 2, 3, 4 steps takes us to the number 9. That's pretty straightforward and what you'd expect. But what happens if the result doesn't fit into 4 bits anymore? For example, what if we add 9 and 8? So we start at the number 9 and we start stepping to the right, 8 steps in total. But as soon as we step from the number 15 to 16, the result becomes 5 bits. 9 plus 8 takes us to the number 17, which in binary is 1, 0, 0, 0, 1. But the adder is just 4 bits wide, so it only produces the lowest 4 bits of the result, and the upper bits get discarded. So from this 1, 0, 0, 0, 1, we're throwing away the 1 at the beginning, and we're keeping the 0, 0, 0, 1 at the end. So on a 4-bit adder, the result won't be 17, but it will be 1. The 5th bit of the result is simply ignored. This is called an overflow. The result is larger than the number of available bits, such that we lose the upper bits. Let's try a different number. Let's try 14 plus 4. So we start at 14 and we take 4 steps to the right. So you'd expect to see the number 18, which in binary is 1, 0, 0, 1, 0. But again, the result is 5 bits wide and it overflows our 4-bit adder, so we only retain the lower 4 bits of the result, which in this case is 0010, which corresponds to the number 2. So on a 4-bit adder, adding 14 plus 4 will actually produce 2 as a result. And the same holds for bigger numbers, like 15 plus 15. You'd expect this to be 30, which in binary is 11110, but due to the overflow, we only keep the lower 4 bits, which are 1110, 14. And if instead we add 15 plus 1, we start all the way on the right on the number line, the number 15, and we take a single step to the right, which is going to overflow, and it's going to produce the number 0 as a result. So the overflowing nature of this 4-bit adder actually causes us to never really leave this strip of 16 numbers here. Instead, we wrap around and start back at the beginning whenever we drop out of the right-hand side of the strip. So this strip of numbers is actually much more like a ring of numbers. Let's say we start at 14 and we want to add the number 4. As before, we'll want to take 4 steps to the right, doing a clockwise rotation along this number circle. So the first step takes us to the number 15, and now we're at the end of the original strip of 16 numbers. But since the overflow causes this to be like a ring, the next step takes us back to number 0. And the remaining steps 3 and 4 take us to the number 2. And 14 plus 4 is indeed 2 on a 4-bit adder. So instead of moving along a strip of numbers, we're actually moving along a circle of numbers. Let's look at this from another angle. Let's say we are at the number 15 and we add the number 1 to that. We go to 15 and we move 1 step clockwise on the ring, which makes us land on 0 because the actual result was 16, but it overflows the 4-bit adder and it goes back to 0. So on a 4-bit adder, 15 plus 1 is 0. Now this looks strange. If I replace that 15 with an x, and I asked you what the value of x is, you'd probably say it has to be minus 1, because obviously minus 1 plus 1 equals 0. So curiously, because of this overflowing behavior of our 4-bit adder, the number 15 behaves exactly the same as the number minus 1. So let me write that minus 1 down on the ring next to the number 15. And similarly, if I replace that 1 with a y and asked you what the value of y is, you'd probably answer minus 15, because obviously 15 minus 15 would be 0. And so again, in a 4-bit adder with overflow, the number 1 behaves the same as the number 15. So let me write that down as well. Let's keep exploring. Let's try different numbers. For example, say we are at the number 14 and we add the number 2. We move 2 steps clockwise on the ring and land on 0 again. So again, 4-bit adder, 14 plus 2 equals 0. And again, that looks strange, and if I replace the 14 with an x, you'd probably say x is minus 2. And so by the same line of reasoning, the overflow causes the number 14 to behave exactly the same as minus 2. And if I replace the 2 with a y, you'd probably say that y is minus 14, because obviously 14 minus 14 is 0. So again, the overflowing adder causes the 2 to behave exactly like the number minus 14. And the same holds for other numbers like 9 plus 7. We start at 9, we take 7 clockwise steps, that lands us on the number 0. So again, 9 plus 7 equals 0 because of the overflow. And again, if I replace 9 with an x, you'd say x has to be minus 7 to balance the equation. So again, 9 behaves like the number minus 7. And vice versa, if I replace the 7 with a y, you'd say y has to be minus 9 for the equation to make sense. So the number 7 behaves like a minus 9 in a 4-bit adder. And we can play this game for every number. Every positive number on the ring has a corresponding negative number due to the overflow. So we figured out that every bit pattern can be interpreted as a positive or a negative number. But this introduces some ambiguity. For example, if we see the bit pattern 1011 in our adder or in a register, it's not clear whether this is the number 11, the positive interpretation, or the number minus 5, the negative interpretation. So it's important that we decide which bit patterns we read as positive numbers and which ones we read as negative numbers. And it's customary to use the topmost bit of the number to decide whether it's positive or negative. This is usually called the sign bit, and if the sign bit is 0, we read the number as positive, and if the sign bit is 1, we read the number as negative. This has the nice side effect of splitting the ring in half. The first half of numbers we read as 0 to 7, and the other half we read as minus 8 to minus 1. In programming languages, we usually call these sign numbers because we look at the sign bit to decide whether the sign of the number is a minus or not. And when you don't care about negative numbers, you can just ignore the sign bit and treat all the numbers as positive. And these are usually called unsigned numbers in programming languages. It's worth quickly thinking about how we can actually negate numbers. For example, if we have the number 1, how can we find the bit pattern for the number minus 1? Or if we're at number 5, how can we get to minus 5? Or the other way around, if we are at minus 4, how can we get to plus 4? If I draw arrows between the numbers, you can see that the numbers form a kind of mirror symmetry across this ring. And if we negate the number, we're basically flipping from one side of the ring to the other. And in fact, if we start at the number and we flip or invert all its bits, it takes us to almost the right place. For example, 5 is 0101 in binary, and flipping its bits gives us 1010, which is minus 6. 1 in binary is 0001, which inverted is 1110 or minus 2. 3 is 0011 in binary, which inverts to 1100, which is minus 4. So flipping the bits almost takes us to the right position. We're just off by 1. So if we not only invert the bits, but we also add a 1 afterwards, we should correctly negate numbers. For example, 3 is 0011 in binary. Inverting gives us 1100, and then adding 1 gives us 1101, which indeed is minus 3. 4 is 0100, which inverts to 1011, and adding 1 gives us 1100, which is also the minus 4 that we want to get to. This also works the other way around. Minus 6 is 1010, which inverts to 0101. And adding 1 results in 0110, which indeed is the number 6. So we can negate the number by inverting its bits and adding a 1. This is usually called finding the 2's complement of a number. This is really useful. Inverting bits is a very cheap and simple operation, and adding a 1 to a number is often also fairly straightforward. So the 2's complement is a very nice and effective way to convert a number into its negative form. And this also allows us to perform subtraction with only addition. Let's say we want to subtract b from a. How would we do that? If you think about it, a minus b is the same as a plus minus b, with minus b in parentheses. And we've just established that we can find minus b by flipping the bits in b and adding a 1. So computing the subtraction a minus b is actually the same as adding a plus b inverted plus 1. It's just additions. So this means that I can get the adder circuit of my homebrew CPU to do subtraction simply by inverting one of the inputs and somehow injecting another 1 into the addition. Let's take a quick look at the current adder circuit. It's pretty straightforward. The adder has a left-hand side and right-hand side input, both are 8 bits, and a carry output. Those get summed up and produce an 8-bit result and a carry output. To make the circuit subtract the right-hand side from the left-hand side, we can just negate the right-hand side before we feed it into the adder. And as we've just seen, we can negate the number by inverting the bits and adding 1. So to perform subtraction, we have to invert the right-hand side and add 1 before we feed it into the adder. We don't want to do this all the time though. Ideally, we'd have a control signal that allows us to switch between addition and subtraction. If the control signal is 1, we want to invert the right-hand side and add a 1. If the control signal is 0, we want to keep the right-hand side unchanged. To invert the bits when the control signal is set, we can use an XOR gate. We XOR each bit with the control signal, which makes the XOR produce the original right-hand side if the control signal is 0, and the inverted right-hand side if the control signal is 1. And to add a 1, we can just make use of the carry input. Right now we have just wired the carry input to 0, so we've always been adding a 0 up until now. So to add a 0 if the control signal is 0, and add a 1 if the control signal is 1, we can just connect the control signal into the carry input. And that's it. If the control signal is 0, we feed the right-hand side into the adder unchanged. If it is 1, we negate the right-hand side by inverting its bits with that XOR gate, and we add a 1 to it with the carry input. And the circuit now is no longer just an adder. It's an arithmetic unit that can perform both addition and subtraction operations. Let's go build that. This is the adder that I've built and hooked up to my CPU to allow it to do addition. I've already pulled it back out of the CPU so we can modify it. It's pretty straightforward. It has two 4-bit adder chips here arranged in a 8-bit adder configuration. There's a left-hand side and right-hand side input. It does the addition and it produces the result up here. We also have a carry input and we have the carry output up here. So I can power this up, set the right-hand side to the number 2, the left-hand side to the number 4, and indeed the adder will show a 6 as a result. So that's pretty cool, but now we want to add a 2's complement circuit to the right-hand side input here such that we can turn this into a subtraction unit on demand. Let me add another breadboard at the bottom. Let me connect the power rails first. Alright, and that gives us space to implement the 2's complement circuit. As a first step, let's bring the right-hand side input of the adder here down to this new breadboard so we can wire it up more easily. Alright, so that gives us easy access to the right-hand side adder input on this new breadboard. To perform the 2's complement operation, we need to XOR each of these bits with a control signal. So we need 8 XOR gates in total. So let me add two 74HC86 chips, which contain 4 XOR gates each. That gives us 8 in total that we can wire up. So that's our 8 XOR gates. Let me connect power and ground. One input of each of the XOR gates is going to be connected to the subtraction control signal. So let me connect the A inputs of every single XOR gate here to one single signal. So that's the control signal wired to one side of each XOR gate. Let me add an LED to show the current state of the control signal. Let me quickly check if this works. Let me set the control signal to 0, connected to ground. And then let me set one of the XOR inputs to 1, connected to VDD. And then let me show the results on one of the right-hand side input bits here. Perfect. So I set the input to a 1, and the control signal is low, so that just propagates through the XOR gate unchanged, and it shows up here. And then if I toggle the control signal, we will actually see this input here flip. And as you can see, the input here is 1, but now the subtract control signal is also 1, so the output gets inverted, and we get a 0 here at the input. Cool, so that works. Alright, so all that's left to do is to actually take the new input from down here, the breadboard, feed it through the XOR gates, and then take the result of the XOR gates and bring it up here to the right-hand side input of the adder. So let me add those wires. Alright, so that's the inputs in the bottom right of the breadboard here, connected up to one side of the XOR gate inputs. And then the result of the XOR gates is connected here to the right-hand side input of the adder. And now all that's left to do is to take this carry input of the adder and connect it to the subtraction control signal. That way, when we set it to 1, we're injecting a 1 into the addition, which is what we need for the 2's complement. So that's this wire here. Okay, cool. Let's try a few inputs and see if this works as we would expect. First up, let me connect the new right-hand side input to ground here. And the subtraction control signal, that will set to ground as well, so that's a 0. And the left-hand side we can leave unconnected because it gets pulled down through the LEDs sufficiently, so it doesn't affect the output too much for testing. Let's power this up. So this is a good first sanity check. All the inputs are 0, and we see as a result what we would expect, a 0. Let me put this into subtract mode by setting the subtract bit to 1. Okay, so what we would expect is we have all zeros at the input, and we would expect the XOR gates to flip them to all 1s, but as you can see, we're missing a 1 here. So there's probably a cable missing. Yep, that one is not connected to the output of its corresponding XOR gate. Let me go fix that. Alright, much better. So we have all zeros at the input. The subtract line is set to high, which means the XOR gate is inverting all the zeros to a 1, which means we get the all 1 signal here as a right-hand side input. But then since the subtract signal is high, the carry input of the adder is also high. And so this adds 1 to this value here, which overflows into the 0 we see at the output here. So all in all, that seems to be working. If I toggle the subtract line and we have a 0 at the input, we don't see any change in the output because 0 is a 0 regardless of whether it's positive or negative. Okay, that looks good. Let's try some actual numbers. Let me set the left-hand side to a 2 and the right-hand side to a 1. All right, addition still seems to work. 2 plus 1 is indeed 3. Alright, let me switch it to subtract mode where we compute 2 minus 1 and we expect to see a 1 here appear at the output. Very cool, that's actually what happens. So by toggling the subtraction wire here, I can actually switch it from 2 plus 1 equals 3 to 2 minus 1 equals 1. That's very exciting. Let's try something else. Let me set the right-hand side to a 2 such that we can observe this thing go to 0. Alright, that works. 2 plus 2 is indeed 4. And now let me switch it to subtract mode. And indeed the output goes to 0. Let me try a larger number. Let me set the left-hand side to the number 26. And the right-hand side to the number 16. Pretty cool. So as you would expect, the 26 on the left-hand side plus the 16 on the right-hand side is indeed 42. Now let me switch it into subtract mode. And that also works. 26 minus 16 is indeed the 10 we see up here. Okay, let's try to get some negative results. Let's start simple. Let me set the left-hand side to a 4. And the right-hand side, let's set it to 5. Okay, and as you expect, 4 plus 5 is indeed 9. Now let me switch it to subtract mode. And that also works. 4 minus 5 is indeed minus 1. And as we figured out before, the all 1's value is indeed equivalent to a minus 1, because all that's needed to make this a 0 is to add a 1 to it, and that it will overflow to the all 0's value. So this behaves like a minus 1. That is pretty cool. Let's try some bigger numbers. Let me set the left-hand side to 10, and the right-hand side to the number 42. Okay, and that seems to be working. 10 plus 42 is indeed the 52 we see up here. And now let me switch it into subtract mode. And that also seems to work. The 10 minus 42 we have here is indeed the minus 32 we get as a result. And finally, let me see if we can negate numbers. Let me set the left-hand side to all zeros. And let's set the right-hand side to maybe the number 6. All right, so 0 plus 6 is indeed 6. That works. Let me switch it into subtract mode, which is more like a negation now because the left-hand side is a 0. And so 0 minus 6 is indeed minus 6 as a result. And so by setting the left-hand side to 0, we can use this circuit as a negation circuit, where we can go back and forth between 6 and minus 6. All right, that looks very promising. Let's do a more extensive test with my circuit tester PCB. So let me connect the tester to the breadboard inputs and outputs so we can actually test it. First up, let me connect the right-hand side input, then the left-hand side, and we also want to be able to drive the subtraction control signal here. And then we want to be able to observe the result and also observe the carry output. And power we can also take directly from the tester. Now let me connect that up to my computer and let's go and update the tester script such that it also checks the addition functionality. Alright, so let me up the tester script and let's modify it such that we can also test the new subtract functionality. Down here we have a loop where we just iterate 1,000 times and we send random inputs to the circuit and then check whether it works. And so let's go modify this check function. And so this carry input of the adder, we've wired up to the control signal, which chooses between addition and subtraction. So this is no longer a carry input, this is the subtract control signal. And here is where we computed the expected result of the adder. And the adder was pretty simple. It was just the left-hand side plus the right-hand side plus the carry input. With this sub-control signal, we now have two different modes of operation of our circuit. If the sub-control signal is 1, we are inverting our right-hand side and we're injecting a +1 through the carry input. And otherwise, we are doing just the plain old addition of the left and right-hand side, and the carry input is 0. And then down here where we print the lines, let me get rid of the plus symbols here because we're now switching back and forth between addition and subtraction, so this might be confusing. That should be all that's needed. Let me go and run this tester script, which should put our new add subtract circuit through its paces. Alright, pretty sweet, so that seems to be working. We checked the case where the sub-control line is 0, so we did plain old addition. And we checked the case where the sub-control line was 1, so we actually did subtraction and we subtracted the right-hand side from the left-hand side. Cool, so that works. So let me go back to the CPU and actually take this adder subtractor circuit and integrate it back to the CPU so we can actually make use of it in an instruction. So that's the CPU as we have left it. When I remove the adder board here, you can see we have the right and left hand side inputs and the result wire here dangling. So let me bring the updated adder circuit back in and let's hook it back up. Okay, let's first connect the result of the adder back up. Next up, this is the left hand side. This is operand number 1 that we're reading out of the register file. That's that hooked up. And then we have the right-hand side input here. This is operand number 2. And this one will go to this new input of the 2's complement circuit. Then there's power and ground. But now, since we've extended the adder, we also have this control signal, which gets displayed on this LED down here. And this control signal we need to hook up somewhere. Ideally, we just wire this to one of the instruction bits as we used to do, but we've actually run out of instruction bits. If you remember last time, we actually used the last unused bit in the instruction to decide whether we want to write the ALU result back into the register file or not. So we don't have any unused bits anymore. But I think for the time being, we'll just use bit number 12 in the instruction here, which is in the upper part of the instruction. That bit is actually only used for the immediate. All other instructions have had that set to a 0. This will break the add with immediate instruction, which actually uses the immediate bits. But that's not too bad. We'll fix that soon with some instruction decoding. But for the time being, let's use bit number 12 for that. Okay, so that's bit number 12, which is the fourth bit from the top, wired up to this new subtraction control signal. Okay, so that's the new arithmetic unit hooked back up to the CPU, and this new control signal all wired up. So let's define a subtract instruction, and let's go write a program that actually makes use of it. So first things first, let me go update the instruction set architecture document, because we have this new control signal that allows us to switch between addition and subtraction. First up, let me describe this new control signal that we have. We've wired this up to, it's wired up to bit number 12, which is all the way up here in the middle of the immediate bits. So this now controls the arithmetic logic unit. If this bit is 0, we're doing an addition, and if it is 1, we're doing subtraction. The add instruction has this bit set to 0, so our arithmetic unit is properly going to do an addition. But now we can duplicate this add instruction and just set this bit to 1, and we will effectively do a subtraction. Okay, that was pretty easy. So addition and subtraction work in the exact same way, and the encoding is also almost identical, except for the 12th bit up here, which decides which function our arithmetic unit is executing. And this is going to be a very common pattern where instructions have a very similar encoding, but there's a few bits in there that indicate what the actual operation is that a certain functional unit is doing, in this case the arithmetic unit. And now one of the downsides of using a bit up here in the middle of the immediate bits to control whether we do addition and subtraction is that we no longer can have this add with immediate instruction, because the add with immediate actually interprets the uppermost 8 bits of the instruction as the immediate operand, and then it wants to perform addition. But at the same time, we have wired this 12th bit up to the control signal that switches between addition and subtraction. So if we left this add-I instruction in there, depending on what immediate you would feed it, it would switch between addition or subtraction, which is a pretty useless operation. It would be very difficult to control what exactly it is doing. So let's get rid of add with immediate for now. We'll add it back in later on when we have some instruction decoding, but for now we don't need it. Okay, so that's the new instruction set encoding. Let's actually go and add this new instruction to the assembler. First up, we'll want to add it to the test program that we've been using in the assembler. And then down here, we've been doing some addition testing. First of all, we no longer have this add with immediate instruction available, so let's just replace this with a load immediate. And then after the addition, let's also just add in a subtraction. Okay, let's run this through the assembler and let's see where it breaks. Alright, so the assembler has no idea what the subtract is, so let's open up the assembler and let's go fix that. Okay, first let's fix the instruction parsing, because this is what fails right now. It doesn't even know what a subtract exactly means. First up, we delete the add with immediate, which is no longer supported. And then we'll just duplicate the code for the add instruction here. We call it sub. It's going to parse 2 registers, just like the add. And then we'll need to use the sub opcode. Let me add this opcode. So instead of add I, we'll have sub. Let's see if this works. Okay, so we have a use of the add-I opcode that we need to get rid of. Okay, add-I is no longer supported, but that's a good opportunity to implement encoding for the sub instruction. Now, if you recall, add and subtract are actually identical, except for this 12th bit where add needs a 0 and subtract needs a 1. So let's add this to the assembler, such that when we encode add or subtract, we're actually setting this 12th bit to the correct value. So starting at bit offset 12, let's encode 1 single bit. It's going to be 0 for the add, and it's going to be a 1 for the subtraction. Okay, let's give this a try. Okay, it looks like in print instruction, we are still using the add-I opcode. Add-I no longer needed. Let's add printing for the sub instruction. Okay, so the assembler seems to be happy now. Let me scroll up and look for that sub instruction. It's right up here, and it seems to be working. As you can see in the upper 4 bits here, the add instruction has a 0 and the sub instruction has a 1. And if we go back to the instruction set architecture and we compare this, indeed, the add instruction has a 0 in the upper 4 bits and the sub instruction has a 1 there. So now that we have a new instruction, let's look at the programs we already have. So this test.s we've been using to test the assembler. And last time we wrote up this test_add program here, which just tested the addition functionality. And I think we want a test_sub program that just checks if the sub instruction works. At the beginning, let me clear the registers to 0. Let me steal that from the other program. Then let me insert 2 NOP instructions so we can separate the parts of the program a bit. And then let's go and actually test a few things. First, let me actually test addition with negative numbers because we didn't do this the last time. Let me load a few numbers into registers. For example, 42, minus 24, and maybe minus 53. And so let me add R0 into R1. And what do we expect here? R1 is minus 24, and we're adding to that R0, which is 42, and that's supposed to be 18. Let me also add the binary representation. And then let's do the same thing with R2. So we are adding to R2, which is the value minus 53, the value in R0, which is 42, and minus 53 plus 42 is minus 11. This doesn't even need the harder changes we just made, but it's good to check these negative numbers to see if the adder works with these 2's complement numbers that we've just discussed. So now let's actually do some subtraction. First up, let's just subtract 2 positive numbers, the simplest case. Let me again load just 3 numbers, maybe 19, 24, and maybe 13. Let's do the same thing as we did before, but this time we use subtraction. So let me compute R1 minus R0, and R1 is 24, minus R0, which is 19, which we expect to result in 5. And then let's do the same thing with R2. Let's compute R2 minus R0. R2 is 13, minus 19, which should give us minus 6. Okay, so that's with positive input numbers. Let's try with one of the numbers negative. For example, let's try to subtract a negative number. Right now, R1 should be set to 5, and R2 should be set to minus 6. So let's actually just subtract the 2, and let's see if that works. So let's just compute R1 minus R2. So R1 is 5, and minus R2, which is minus 6. So that's a minus 6, and that's the same as 5 plus 6, which should give us 11. Let me maybe clear R0 here as well. Let's do it the other way around. Let's make the left-hand side negative and keep the right-hand side positive. For example, let's compute minus 9 minus 6. So let me load minus 9 into R0 and 6 into R1. And then let's subtract them. So that's R0 minus 9 minus R1, 6, which should give us minus 15. Okay, last but not least, let's try with both arguments negative. Let's use 2 numbers, maybe minus 18 and minus 13. And let's reuse this minus 15, which we have in R0. And let's subtract maybe R1 minus R0, and that's going to be R1 minus 18 minus R0, which is minus 15. So that's a minus 15, which is the same as minus 18 plus 15, which should be minus 3. And then let's do the same with R2. R2 is minus 13, minus R0, which is minus 15, so that's a minus 15, which is the same as minus 13 plus 15, which should be a 2. Okay, so that should be a pretty good test. We subtract positive input numbers and produce a positive or a negative result. We tried the same with a negative right-hand side. We try the same with a negative left-hand side, and then we try with both sides negative input numbers, and then we get a negative and positive result. So that should put the subtract mode of the adder through its paces. So after these tests, let me add another 2 NOP instructions to separate things again. And let me clear the registers R0, 1, and 2, which we've filled with data. R3 should still contain a 0, so we can just move from there. Now let's also compute something more interesting. The last time for the adder we used the Fibonacci sequence. Let's pull that back up. So here we were running through the Fibonacci sequence and we were filling up the register file just with these Fibonacci numbers. But I think we can do the opposite if we start at the 2 largest Fibonacci numbers that we have. 233 and 144, we should be able to run backwards. Instead of doing addition, we do subtraction, and we should be able to go all the way back to the beginning. So let's code that up. So first up, let me load the two largest numbers, 233 and 144. And then let's subtract the smaller one from the larger one. So that's R0 minus R1. And that should give us 89. And so now we have 144 in register R1. And we have 89 in register R0. So let's compute the larger number, which is R1, minus the smaller number, which is R0. And 144 minus 89, that should give us 55. And then we repeat the pattern. 89 minus 55 should be 34. Then 55 minus 34 should be 21. Then 34 minus 21 should be 13. 21 minus 13 should be 8. 13 minus 8 should be 5. 8 minus 5 should be 3. 5 minus 3 should be 2. 3 minus 2 should be 1. 2 minus 1 should be 1. And 1 minus 1 should be 0. Cool, and that's all the way to the beginning of the Fibonacci sequence. And then after that, let's just halt the processor. Okay, that looks like an interesting program. So first up, we clear the register stack to 0. We check that addition works with negative arguments. We check subtraction with positive arguments, subtraction with the negative right-hand side, negative left-hand side, both sides negative. And then we have a reverse Fibonacci sequence where we go from the two largest numbers we can represent in 8 bits all the way down to the two initial numbers, 0 and 1. Pretty cool. Let's see if the assembler can actually do something useful with this. Okay, so that does something. There's a big binary blob, which is the program that our CPU can execute. And if I scroll all the way up, we can actually see the program. This is clearing out the registers. These are the tests for add and subtract. Then we have the two knobs. We clear the register file back to all zeros. And then this is the reverse Fibonacci sequence. And then for each instruction, you can actually see it's been encoded properly. Very cool. So that seems to be working. Now in this directory, we have the assembler, and we're starting to build up different programs. Let me add a make file that makes it easier to assemble the programs into binary form, which we can then write to the program memory. This is going to be pretty straightforward. We'll add a rule how every .bin file can be generated from a .s file. And the way we do this is we just run it through the assembler. We pass in the .s file as the input. We tell the assembler to output to the .bin file. And then we want to make the binary file exactly 128 kilobytes in size, because that's the size of our ROM chip. And now we should be able to use the make command to actually build the subtraction test binary. And yeah, that works. As you can see, make executed the assembler. It passed in the .s file as the program, instructed the assembler to output to the .bin file, and then configured the size of the binary appropriately. And now, if I take a look at the directory, there's now also this test sub.bin that got generated. And if I run make again, nothing changes because we haven't changed the source program. But if I go in and change the test sub.s program, just change a comment, and if I call make again, we actually get an updated program. But when I rerun make, nothing happens. Okay, pretty cool. This is going to be very useful in the future. So all that's left to do is to write this new test program to the program memory of the CPU and then give it a spin. Cool. Let me put the program memory back into the CPU and then let's run the program. Alright, so that's our new program stored in the program flash memory here. Let me power this up and let's give it a try. Let me step it out of reset. The first part of the program is going to clear the register file to all zeros. So first we're loading the immediate 0 into register R0. And then we're moving that 0 value from register R0 into R1, then R2, 3, 4, 5, all the way down the stack. So that's move R0 into R1, move R1 into R2, move R2 into R3, move R3 into R4, R4 into R5, and R5 into R6. Alright, that worked. Now we have two knob instructions that I'm just going to skip over. Now that the register stack is cleared, we're going to test a few of our arithmetic instructions. So to get started, we're loading 3 numbers into the register file. We're loading 42 into register R0, minus 24 into register R1, and minus 53 into register R2. And that looks like it works properly. We have a 42 in R0, we have a minus 24 in R1. As you can see, the sign bit is set up here, and also for register R2, so these two are negative numbers. So this is a minus 42, and then register R2 has a minus 53 in it. And so next up is an add instruction. We're going to take the 42 in register R0 and add it to the minus 24 in register R1. And then we're going to store the result back into register R1. And so minus 24 plus 42, same as 42 minus 24, is the value 18. And so when I hit the clock, we want to see register R1 be assigned the value 18. And then as a second check, we're taking the 42 in register R0 and we're adding it to the minus 53 in register R2 here. And 42 minus 53 is minus 11. So when I hit the clock, we want to see register R2 be set to the value minus 11. So addition still works, and if we purposefully load negative numbers into the register with the sign bit set and in 2's complement notation, the adder actually does the right thing without even knowing that those are negative numbers, and we see the correct results appear here in the register file. So next up, we're going to test subtraction a bit, and for that we're loading 3 new values. So we're loading 19 into register R0, 24 into R1, and 13 into R2, and that works. And now we have the first subtraction instruction ever to run on the CPU. We're taking R1 and subtracting R0 and then storing the result back in R1. So that's the 24 here in R1 minus the 19 in R0, which should be a 5, and we want to see the 5 be written back here into register R1. Cool, so that 5 has been stored in R1. Next up, another subtraction. We're computing R2 minus R0 and storing the result in R2. So R2 is the value 13 and we're subtracting the value 19. So we expect a minus 6 to appear here in register R2, which it does. Very cool. Now we're trying subtraction with a negative right-hand side. First up, we're clearing R0 to 0. And now we're computing R1 minus R2. R1 has the value 5 in it, R2 has the value minus 6 in it. And so we're computing 5 minus 6, which is the same as 5 plus 6, which should be 11. So we expect register R1 here to store the result 11 of the subtraction. Alright, so that seems to work. Next up, we're trying subtraction with a negative left-hand side and a positive right-hand side. And so first we're loading minus 9 into R0 and 6 into R1. And then we're computing R0 minus R1. That's a minus 9 minus 6, which should be a minus 15 stored back in R0. And that works pretty cool, so that's our minus 15 here. And then finally, we're doing some subtraction where both the left and right-hand side are negative. So we're loading minus 18 into R1 and minus 13 into R2. And then first we're computing R1 minus R0. So that should be minus 18 minus 15, which is the same as minus 18 plus 15. So we expect to see a minus 3 appear here in register R1, which works. Pretty cool. And then as a second step, we're computing R2 minus R0. So that is a minus 13 minus 15, which is the same as minus 13 plus 15, which is a 2. So we expect the value 2 to appear here in register R2, which it does. Pretty cool. So that seems to be working. So those are the few tests we had for these subtract instructions. Now there's 2 knobs to separate it from the rest of the program. Let me step over those. Now we're clearing the register file back to 0. We're copying register R3, which has a 0 in it, into R2, R1, and R0. That's R2 set to 0, R1 set to 0, and R0 set to 0. Alright, and now we're trying this reverse Fibonacci sequence. First up, we're going to load 2 Fibonacci numbers. We're loading 233 into register R0 and 144 into register R1. Okay, if you remember from the previous program, we actually had a Fibonacci sequence that ran all the way up to 144 and then 233, which was the largest number that we can store. So this is basically now doing the reverse. First up, we're computing R0 minus R1, which is 233 minus 144, and that should be the number 89, which we want to see stored in register R0. And that indeed has worked. That's an 89. Okay, and now we're taking the value in R1 and we're subtracting R0, so that's 144 minus 89, and we expect to see the value 55. Indeed, 55, 89, 144, 233 are all Fibonacci numbers. We're just counting backwards. Next up, we're computing 89 minus 55, and we want to see the resulting 34 appear here in R0. Then 55 minus 34, that's 21 in register R1. 34 minus 21, that's 13 in register R0. 21 minus 13, which is 8 in register R1. 13 minus 8, which is 5 in register R0. 8 minus 5, which is 3 in register R1. 5 minus 3, which is 2 in register R0. 3 minus 2, which is 1 in register R1. Then 2 minus 1, which is 1 in register R0. And finally 1 minus 1, which is 0 in register R1. Alright, pretty sweet. And next up is a halt instruction. So no matter what I do, the processor stops here and the program is finished. So that looks very promising. Those were the initial Fibonacci numbers starting at 233 backwards all the way down to 0 and 1, which were the seed values that we used the last time to actually do it the other way around and add up the Fibonacci sequence. So that's very cool. The addition works with negative numbers, but more importantly, the subtraction mode works that we've just added, and we can subtract a lot of numbers, and we actually managed to get the Fibonacci sequence working in reverse with this subtraction here. Now we're at the halt instruction, so I can switch the processor into run mode. And it isn't really doing anything, but let me reset it. Now the program starts from the top, it clears the register stack, then it does the tests with the add and the subtract instructions. Then it clears the register file, and now it does the reverse Fibonacci sequence all the way down to 0 and 1. And we run into the halt at the end of the program, and we're basically done. The processor stops. And notice how I can see some toggling here, even though the processor is actually halted at the moment. That's because we're actually using an 8-bit program memory here, but we're reading out 16-bit values. And what we're doing is, in the first half of the clock cycle, we're reading out the first 8 bits, and in the second half, the other 8 bits. And the way we've implemented this with a latch here actually makes the instruction toggle halfway through the clock cycle. We'll fix this eventually, but not today. So as it turns out, overflows in an adder are extremely useful. They allow us to fake negative numbers and subtraction just by pretending a number is negative. We have extended our adder here with a 2's complement circuit, which converts numbers to the pretend negative version by flipping all the bits and then injecting a 1 into the addition. That means that our adder has now evolved into an arithmetic unit that can be configured to perform both addition and subtraction. And our CPU has a subtract instruction now, which we've thoroughly tested with this new program. We've sacrificed the add with immediate instruction because we don't have enough instruction bits right now, but we'll bring it back soon. In the next episodes, I'd like to build out the ALU a bit and maybe look at shifting the bits inside a number around and doing addition and subtraction on larger numbers more than just 8 bits. This is coming along very nicely. I can't wait to have more ALU instructions available and be able to actually compute some meaningful things on this processor. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.